Hi, I'm Matt Mead, Governor of Wyoming. I want to welcome you to the NCAR Wyoming Supercomputing Center. We are very pleased to have this supercomputer here in Wyoming. I'm here with my friend, former Governor Freudenthal. Governor Freudenthal.
Governor Mead.
My name's Dave Freudenthal, and I was governor from 2003 to 2011. The development of this project was a partnership that came together with great energy and enthusiasm, both from the state of Wyoming and from the federal government. This facility is important because it will add to our knowledge about the interaction of storms, weather, drought, wildfires, energy production, agriculture, and all of those things that are important in the West, but they're also important in the United States and throughout the world.
What is the atmosphere? The atmosphere is a very thin layer that surrounds the entire Earth. It's about 6 miles thick, and it contains everything: oxygen, nitrogen, the air we breathe, and almost all of the weather. Clouds, thunderstorms, tornadoes, hailstorms, hurricanes, blizzards, and rainbows. The atmosphere also carries pollen, smog, air pollution, and the greenhouse gases that cause global warming. Sometimes the atmosphere literally comes down on our head, whether it's low-lying clouds or a fog-like mist. The atmosphere is dynamic, it's beautiful, and it's constantly changing. Our discipline cannot survive without supercomputers. They do things like simulate the climate, help us predict where severe weather will occur, what storms will produce tornadoes, floods, help us figure out where air pollution will be transported, and really start looking at things that affect people's daily lives, if not for their future generations. We try very hard to make our science relevant to the general public.
Original supercomputers were room-sized and really didn't have any more capability than today's cell phone. Weather models weren't very accurate. A severe storm looked like nothing more than maybe a small blob on a screen. Today, we're much better with the accuracy, but greater accuracy requires more computing power. More computing power requires more processors. This facility has been designed to handle that demand into the future. A computer is nothing more than a bunch of circuits. When a circuit changes its state, converts from a 0 to a 1, it gives off heat. For this facility, we use tens of thousands of processors. Computers malfunction when they overheat, so it's critical that we keep them cool. We've taken advantage of the region's climate. This building brings in cold air, exhausts the hot air, and we also recycle the heat throughout the rest of the building. This facility was designed to be energy efficient and flexible. Some of the key energy efficiency features are floor vents, this large fan wall, and we also take advantage of renewable energy such as wind.
This is actually very technologically complex. There's 72,000 individual processors located on over 4,000 nodes, and then these nodes are all interconnected via a high-speed interconnect fabric that lets them communicate with each other. So it actually makes it one computer. Cable management, as you can see behind me, is a huge challenge here. There's over 12,000 cables. Every cable is labeled, it's tested. So despite the angel hair pasta look, there's a lot of order in the disorder. One of the biggest challenges when you have all of these processors trying to talk with each other is moving data between them. So there's really two things we worry about. One is latency and the other is bandwidth. Moving data around is a lot like plumbing. Latency is the amount of time you wait for that hot water to get from your hot water heater to your sink. Basically the time from point A to point B. Bandwidth is like the gallons per hour you can move through the pipe. So it's the volume of data that you can move. At any given time on this computer, we're able to move billions of bytes of data through tens of miles of cable on this system. And moving that data is just critical to actually doing the science.
Imagine millions and millions of grid boxes spread out over the Earth in a mesh in 3 dimensions, stretching from the bottom of the ocean to the top of the atmosphere and into outer space. And these grid boxes are where the physical quantities are stored. For example, temperature, pressure, and wind velocities. And they're calculated upon using the laws of physics in chemistry and thermodynamics. And each processor takes a relatively equal chunk of these boxes and works on that part of the problem. So in the same way that ants in an ant colony might work together to accomplish something, these processors all team up and use the network to work on the same task. However, the way the laws of physics work, you need to actually talk to your neighbors to find out what's going on next to you to do these calculations, and that's where the communication comes in. It would take a person working with a hand calculator literally hundreds of millions of years to do the calculations that one of these supercomputers can perform in a matter of a few seconds. All these connections between the different processors that are signaling each other is in many ways analogous to the way neurons work in your brain, working together to form a sentient being.
Supercomputers and the computational models that we run on them allow us to study important issues related to climate, to weather, the atmosphere around us, to energy, to water and ecosystems, to how all of these systems interact with the human system. What we as humans do greatly affects the world systems. And supercomputers allow us to model these Earth systems and take into account complexities and interdependencies that we've never been able to before. Supercomputers are one tool. It augments experiment and theory, but because of the complexity of these problems, supercomputers are in many ways the most efficient and the most powerful tools at this particular time. At the University of Wyoming, we are already integrating the use of supercomputers into our classes, both at the undergraduate and the graduate level. We find that supercomputing allows our students to have a real interdisciplinary experience and provide them with skills they'll need for their future careers.
One example for how supercomputers help us better understand the Earth system is by modeling the sea ice and looking at its influences on the atmosphere and on the ocean, we can get a good sense of how variations or long-term changes in the Arctic sea ice pack are going to affect the atmospheric conditions, precipitation, rainfall, snowfall, and the general climate. Sea ice is incredibly important for the Earth's climate. It acts kind of as the Earth's refrigerator. Sea ice is a very bright reflective surface. What that means is that it reflects a lot of sunlight away from the Earth's surface and causes the Earth's surface to cool. So when you replace ice with open ocean, you lead to a situation where you absorb a lot more heat. And that gets you in this vicious cycle where you absorb more heat, you melt more ice, you absorb more heat, and so it just acts to amplify warming in the system. Our models solve the equations that describe how sea ice moves, how it melts and grows in response to winds and ocean currents, and how it regulates the transport of heat from the ocean into the atmosphere. So the sea ice component of our climate models describes all of these different aspects. And that piece interacts with an atmospheric model, an ocean model, a land surface model, and all of those parts of the climate system interact. They exchange heat, they exchange water, precipitation. We have equations that describe all of these things. What this requires is a vast amount of computational power, which means that we have to use supercomputers to study this problem. Supercomputing gives us the capability to look at the Earth using a virtual laboratory. Supercomputers allow us to study the interconnectedness and the intricacies of coastlines, urban areas, habitat, animals, and the food web and biodiversity. Supercomputers are allowing us to look at all these different aspects of the problem, how all these things are interconnected, how they impact and modify each other. A better understanding of climate science is critically important for people because we have to live in this climate. So we need to understand those variations, those changes, those interconnections because it affects us.